Hey folks, Todd Coburn here with your Aerospace Structures series. This video is on CROD elements. I'm actually going to break this topic up into a few pieces because we're going to look at a bunch of things with CRODs. Think back, you're going to want to first make sure you watch Lecture 1, which is basically an introduction to NASTRAN. It walks through all the pieces, step-by-step pieces of how to create the most simple NASTRAN deck. And these same pieces and approach can be used for nearly any model with slight or more significant deviations. Now, in that first video, we talked through our first model, and it was a model made of CRODs. So we actually covered a number of topics about CRODs already. So you're going to want to make sure you watch that first, and now we're going to build on that. And then with the other subtopic videos for Lecture 2, we'll look at how to do various kinds of analysis and other types of elements, and we'll look at them at how they relate to this simple CROD model. Later, we'll look at their capability in more depth using other elements, but now we can actually prepare ourselves by learning about how many of the few of the basic elements are used in the simplest model and how some of the specialized elements are used in the simplest of models. So stay tuned. Let's take a look. Once again, we're building on what we learned in Lecture 1 about our basic model, and we're going to focus on the CROD element part. So we're going to move quickly through the pieces we already covered. So stay tuned. So first, let's take a look. Going back, you should probably watch video number 1, Intro to NASTRAN, which is going to go over the basic elements of a NASTRAN input deck. And what we looked at was a simple rod model there as well. Let's say we have a simple rod loaded in tension. One of the skills that we're going to need to learn, and you should do with nearly every model, is first sketch your model with how you're laying it out. You're going to plan out your model, where it goes, where the parts are. We talked about that in the last video. And sketching the model, that means you're going to draw your coordinate system as we see here. We're going to draw your nodes and identify them. Now on a larger model, you're only going to do a subscale part of that. On a smaller model, you can often draw all the parts, all the idealized elements. Then you're going to draw your elements, like your rod. In this case, we only need a single rod for this model. Identify it and show what the orientation is, like your first pick and second pick for the nodes. And then your constraints and your loads. So just like this, we need to be able to look at a structure and quickly sketch a finite element model idealization, where we're idealizing the points and the elements that will be used, followed by the loads that are going to be applied and the constraints that are going to be applied. Now, what we saw before was a NASTRAN deck like this. Remember, we have the delimiters between our executive, case control, and bulk data decks. Our executive deck can be as simple as that. We're often going to want that sort, echo equals sort command. You're going to want some titles on most models. And then you'll lay out your subcases where you're identifying the set IDs for the loads, the constraints, and then all the data requests. You're going to want to come back to either the FO6 file for looking at the output yourself, or to like an OP2 file for returning those results to NASTRAN or to PATRAN or FEMAP. You're going to identify your nodes, as we discussed in the first video, and the location of those, and then you identify your elements. The CROD goes from 1 to 2. Now remember, the CROD element has only axial load carrying capability and torsion capability. This means, since it has axial load capability and there's nothing between it, it will always be a constant force member. NASTRAN will only report one force and one stress for this rod. If the load changes across the rod because of something like a shear panel, you'll have to see the shear panel video for that, then you're going to have to actually add in information from the shear panel to get how that load changes across the element. Because NASTRAN will only report a single load for the rod element. because it's a constant force member with nothing attached between. And if there's some element that applies load between, like a shear panel, you're going to have to do a little bit of tweaking of the results after your model run, as we discuss in our C-shear video. So for this model, we've got our rod definition. The rod is ID1, using property ID1, going from grid points 1 to grid point 2. Remember, go back to video 1. I walked you through this in detail as we talk about our first final model and the simplicity of that, and we cover a lot of these topics. Then we come to our P-rod card, which is ID1, which calls out material card ID1. So here's the material card that's going to be used with ID1, and then the area. And there are other inputs that you can put in. We'll talk about those in a moment. Your material card, which is ID1, which ties it to this particular property card, which ties it to this particular C-rod. Then you have the modulus of elasticity, the shear modulus, and then we could have specified the Poisson's ratio and a number of other things. Now remember, with NASTRAN, since Poisson's ratio, the elastic modulus and the shear modulus are all related, usually NASTRAN frowns on you reporting all three because they usually won't completely fulfill the relationship between the three that's common in most materials we're using in practical engineering applications. So usually reporting two of those or inputting two of those and letting NASTRAN calculate the third. This is the force that's applied. This is a force. It's got set ID 1. We see the load card says it's going to use all applied loads that have a set ID of 1, and this 1 here places this force in the first load set, the one that will be used. In this case, there's only one force card, but there could be a bunch of forces and moments and other things with the same set ID. Then we're going to normally leave this field blank. We'll talk about that in another video. There's the magnitude of the force and the unit vector, which is showing the direction, which must be real. Must be real, must be real. These have to be integers. And then our constraints. These are called single point constraints. This identifies the set ID. This SBC here in the case control, as we discussed in the first video, says that all constraint cards with a set ID of 1 will be used for this analysis. So now it looks here, this card is defined in that set 1, therefore it will be active for this particular run in subcase 1. We notice at first this particular card allows us to define two constraints at two nodes. At the first node, these are the constraints, which means completely fixed. At the second node, these are the constraints, which is completely fixed except it allows axial load. Now, some folks might argue this is a rod and it can't translate all these 6 degrees of freedom. But remember, as we talked about before, you typically in NASTRAN want to over-constrain. In this case, all we really need is to restrain the one direction to keep it from moving. But if you only do that, there's a fair chance that NASTRAN will bomb and not give you a fatal error and not solve it due to mathematical difficulties. So the way to get around that is to completely fix that node. And this rod, the rod element only has axial and torsion capability, so all it really is using is that one constraint and that 4 constraint. All the rest are just keeping the problem from becoming singular. At the far end, we're also removing all degrees of freedom that we don't need, which includes translations in the other 2 directions and all rotations, even torsion, because we didn't apply torsion, there's no need, and we didn't actually give it a torsional constant. So if we didn't have that 4 constraint, we could have an issue with NASTRAN as well. So here's a little simple NASTRAN bulk data file for this simple rod, and we looked at this in video 1. So it's kind of refreshing us to where we're at, and we're going to kind of step from here as we explore some of these other ideas. So let's talk about other ways to use CROD elements in more greater detail. Okay, so let's look at a simple truss. Let's say we have a truss like this. We've got a pin here on a roller joint. we have an applied load, and these three members are all rods. I mean, that's all we need. This is the same kind of problem as you can solve in statics. In fact, if you want to practice these, so I'm working on providing more example problems in my videos, but one great way to practice using CRODs is to grab your statics book, which you never should have sold back, because if you're in structures, you're going to need to refer to that at times. You can go in there. There's a bunch of example problems, and a lot of them have the answers in the back, like if you're using Beer and Johnson or Merriam and Craig or one of those books. And you can pull up any of those truss problems that you had trouble solving back when you were in school, and you can do a simple model, NASTRAN model, and you can try and match those results. And it should match every time, and it should be easier than doing it by hand in most cases, especially as you get more and more proficient. So here's a simple model or structure, and we're going to model this puppy up. So if we want to identify this, we'll call this grid point 1, we'll call that grid point 2, we'll call that grid point 3, and we'll apply our degrees of freedom, which basically is going to fix everything except the motion we want free, that 2 direction. We're going to allow this to roll in the 2 direction. This is going to fix everything. Now, I've had some comments on videos and from students where they say, oh, wait a minute, that's a pin. You can't give it a 6 degree of freedom. True, it is a pin, and putting a 6 degree of freedom there, 4, 5, 6, actually removes all ability to rotate as well. So it's true on the surface that this should be a 1, 2, 3 and a 1, 3. 1, 3 at grid point 1, 1, 2, 3 at grid point 2. However, remember, NASTRAN is just going to create a mathematical set of equations that it's going to try and solve, and it will have issues often and cause fatal errors if it finds there's something that's unconstrained. So we're going to over-constrain this while tying in those 4, 5, 6 directions makes that so it can't rotate. If you look at this model, we're going to model this with 2 rods, and rods can't resist twist. They can't resist out of plane rotations, only around the element rotations. That means putting these fixities doesn't change anything because the rod element can't translate those. So fixing these allows us to remove the chance of a fatal error, but also allows it to behave as it's supposed to behave. So 4, 5, 6. Now, if we has no effect. If we had modeled this with C bars or C beam elements, then these constraints would be incorrect, because what that would do is those bar and beam elements can then translate and move moments into the joint, which is what these will now pick up. But a rod element can't translate moments. It can only translate twist and a load along the axis of the rod. Therefore, this is probably the best way to model this constraint. And at this node, now we're going to fix this in the 3, 4, 5, 6. So we're fixing the rotations and the translation in the Z. We've actually got no elements in the Z. We've got no stiffness in the Z. So just removing that degree of freedom with the 3, as we did at all nodes, is good. So if you look at this, we have a planar model. We can expect it to translate, to move and in the plane of the model, but there's no information for out of plane. We don't need that, so we've removed all 3 translations. We have no torsional capability about the x-axis, so we're moving 4 from everything. We have no moment stiffness in the y direction, so we're removing the 5 from all nodes. And we have no rotation capability about the 6. Now, if these were beams or bars, by the way, as we said, then we wouldn't be able to constrain or wouldn't need to constrain 6 because the bar would tie these together in that manner. But because these are rod elements, and that's best to so really The degrees of freedom that are most meaningful are fixing the 1 and 2 at grid point 2, the 1 at grid point 1, and nothing at grid point 3, or C. However, because of the constraints and the elements that we're using, these constraints are probably the best way for this simple model. Okay, here's our little NASTRAN model then. You can see we've got our executive deck, looks identical to before. Our title's identical to before, except for changes in the naming. We're using, as we said before in our first video, we're generally going to use just one subcase. And we're generally going to have just one set of constraints and one set of loads. So calling out SPC1 and load 1, and then giving all the applied loads, the ID1, the set ID1, and all applied constraints, set ID1. We see our grid points here. This is the same as we've done before. We just now have our first point at 0, 0, 0, our second one at 0, 1, 68, 0, and our third one at 90, 120, 0. Remembering that the locations need to be real numbers. The IDs need to be integers. Our CRODs, we're going to find 1 going from 1 to 2, 2 going from 1 to 3, and 3 going from 1 to 3, and 3 going from 2 to 3. Okay, and then we've got our PROD. We're only giving it axial area. We've got our material card. Notice we're only calling out the material, the modulus of elasticity. That's all we need in this model. Sometimes NASTRAN will give a warning if you don't give the other values. FEMAP tends to like all the values to be specified. Your SPCs, this time we're using the SPC card. We're just going to tie down one node for each. Remember, you can do multiple nodes using the same card if the constraints are the same. So we put in our constraints here. At 1, we've got 1, 3, 4, 5, 6. At 2, we've got 1 through 6. At 3, we have 3, 4, 5, 6. Our force, remember, is in set ID 1. At grid point 3, it's got a magnitude of 5,600 pounds, and it's pointing in the down, the negative y direction. There's our simple model. Now let's go ahead and take a look at the results. We're going to get our SPC forces. This is going to give us the forces at each constraint. So at node 1, this is the SPC force resultant. So this is adding up all the constraints, and this should match what we have applied. You can see we've got a force that matches here at in the y direction, and we have a moment since that force is not applied at the origin. So that's giving us that force times this distance for your moment. And we've got our forces in the x direction are summing to 0 as they must. Okay. Our displacements, we get the displacements at each point. That makes sense. And you can match these. These will be difficult to match by hand, so NASTRAN will give you a better estimate than most hand analyses could do. You can get your forces at the constraints, and this is reading right out of here. You can see at node 1 we have a force of 3,000 pounds in the positive direction, negative 3,000 at node 2, and we have this 5,600 in the y direction at node 2. So we've got our x and y values at grid point 2, which is at B here. Our forces and the elements. This is, so what can we match? So if you analyze this by hand in statics, so you statics folks that want to get into finite element modeling and also increase your understanding of statics, you can do this, make this little model. You would create your model. You're going to predict by hand your internal forces in the rod. So what you do is first solve for your constraints by hand, summing your forces and moments, and then you use the method of joints or sections to calculate what the force is in each rod element. And then you can check your forces directly against this. Tension or compression. Compression means, negative means that thing's in compression, and check your results. You're not going to be able to check your displacements, but you can check your reactions using the forces of single point constraint. You can check your internal forces. This is a really good tool to make sure that your statics analysis is right, and also to make sure that your NASTRAN analysis is right. And once again, you can just check your answers against the book from your statics book if you're just an industry professional trying to get familiar with NASTRAN and wanting to practice so you understand how to do this quickly. All final analysts should be able to open up a BDF and understand precisely what ROD elements are in there and what their properties are, what their materials are, and what they're going to do. They should be able to pull up the F06 file and quickly identify what's the axial force in the rod, what's any torsion in the rod. There's no torsion in this particular one. What are any margins of safety if you have that information in your material card? We'll talk about that later. And then also stresses, just P over A kind of stresses. All this can be matched by hand, and you should be a master of this if you're doing fine elements in industry. Whether you're using NASTRAN directly or whether you're using Patran or FEMAP to create your NASTRAN models, you need to be proficient in identifying what elements those tools are making, how they're using them, and what the results are coming out of them. Okay? All right. So let's go ahead and take a look at some other ideas, some more capabilities of the rod element. All right, this was our little rod, and let's say we have more information. Here we have the areas of the rods are the same. We now have a torsional constant for each. We have a density of each. This is a weighted density. We have the allowables of each. We get the opportunity in NASTRAN, we can put in the ultimate allowables for tension, shear, and compression, but only one per material card. We have the moduli for this. Here's the allowables. So we have the material properties, 80 KSI for tension, 48 KSI for shear. And then we might say, wait a minute, the material is probably good for at least 80 KSI for compression as well. However, these are long rod, slender rod-like members. And even though we're modeling these as rods and we're giving them no bending capability, we know if they're in compression, since they're long, they're going to tend to buckle. So even though our model can't pick up buckling, we can actually check buckling by checking the allowable of these members. So if we calculate the Euler buckling allowable for each of these members, that's what's shown here. Rod AB is good for 918 PSI. Rod AC is good for 1151, and rod BC is good for 2490. I calculated those by hand using Euler buckling methods. And then our non-structural mass. Now the non-structural mass in NASTRAN is just the mass per unit length. So you can just take your density and multiply by the area of the member, and that gives you the mass per unit length. This makes it easy to distribute a gravity force or loading on the model based on the weight. We'll talk about that in another video. But with all this information, if we had all this information, our case control and executive deck are the same, our grid points are the same, our C-rods are the same, but now our P-rods, because now notice we have the same material, the same area, the same J, so we really only need one material card for that and one property card. So you'll notice each of these property cards are identical, 1, 2, 3. This is property ID 1 is used for grid point 1, for C-rod 1. See, we have C-rod 1 is using property ID 1, C-rod 2 is using property ID 2, C-rod 3 is using property ID 3. Now you'll notice here, you're like, wait a minute, we only need a single property card because the properties are identical. True. However, we have different materials. Even though our modulus and our G are the same for these three elements, notice our buckling allowables are different. So if we want to input the buckling allowables for these, we're going to need to put in 3 different compression allowables. That means we need 3 different material cards, and the only way to get 3 different material cards on a C-rod card is by making separate unique property cards. So The whole reason we called out different property cards, 1, 2, 3, is so we could call out different material cards, 1, 2, 3. So property 1, 2, and 3 are identical except for the call out for the material card. So 1 calls out property ID 1. It has an area, it has a torsional constant, and it has a non-structural mass that we see here, okay? And it also has a, in this case, we have a 1-inch rod, so the R, that value we're going to put in for recovering stresses is the radius, which is 0.5, which I didn't provide in the input data here. We'll talk about how that works later when we get to the element card. Okay, so now with 1 we called out material 1. Material 1 has that E of the material and the G of the material. We don't need anything else in that line. The continuation card brings us here. Remember, this can be blank, this and this, or they can have a character string that matches, which I used to like to do. NASTRAN recommends just leaving it blank, following the card with its continuation. NASTRAN will put those connections in for you. This is now the tension allowable for that whatever element uses this material is going to have this tension allowable 80 KSI. It's going to have this compression allowable, which actually only applies that single rod, not to other materials using this. And it has this shear allowable, okay? Material 2 is identical, except it has a different compression allowable. Material 3 is identical, but it has a different compression allowable. And then we have our constraints and our force. So that is a little more complicated model doing the same thing. Now, all this extra data is not going to help us with anything. It's not going to change our results at all. But now, because we identified the allowables, we're going to get to see margins of safety. Okay? So let's take a look. First, we're going to look at the material card. We talked about some of the extra capability. This is the full material card. Notice we have the name. We have the material ID. That's the same as before. E and G we've been using in Poisson's ratio. Now we have this density. Now, NASTRAN calls this the mass density, which is true. But if you're using US units, you're going to be using pound masses often, which is just like inputting the weight and making it a weight density. If you're not doing a dynamic or vibration problem, then that'll be fine. If you are doing a dynamics or vibration problem, then you need to be careful. Looks like I have a typo in the word thermal. You'll need to be careful because you'll then have to make sure your units are consistent for doing that dynamic analysis. So A is our coefficient of thermal expansion. We'll talk about that. We'll be using that when we get to the thermal analysis piece. T reference, we're going to talk about that when we get to the thermal analysis piece. That's our reference temperature for anything with that material before we apply temperatures. We're going to mostly ignore this damping coefficient. We'll talk about that if and when we get to showing how to do that kind of analysis. And in the continuation line, now normally if you're not putting in allowables, you just leave a single line of input. But if you want to specify allowables for the material, as we did in this model, your second line, you can do that. You can leave this the last field blank and the first field of the continuation card blank, and then you put in your allowables, tension, compression, and shear. And mainly we're going to ignore this. Don't use this unless you're an advanced user. So that is a more complete form of the material card. Usually we're going to use the field 1, field 2, the modulus, the G, and or Poisson's ratio. We're only going to use these two values if we have a thermal problem. This value if we're trying to apply like gravity loads or something, or do some kind of dynamic solution. And we'll only use the continuation card when we're trying to get the allowables of the material. Now, it looks like this is really powerful, but it actually is quite limited because for this material, we only get one tension, one compression, and one shear allowable. So that means unless you're going to make a separate unique material card for each and every element, You could end up with a bazillion material cards to try and get reasonable margins of safety. Also, when you understand more about materials, you realize it's not just buckling, compression, Euler buckling. We also have to worry about crippling and other things. There's a huge amount of analysis going into just figuring out what are the appropriate allowables for this. Most finite element modeling for larger structures should be simple models that basically give you a stiffness to get loads so you can then go and do sufficient hand analysis on your results. Now, there's some really good users out there who will disagree because they're proficient and capable at making a more complicated model and reading it correctly. But for every user that really knows what they're doing and uses a more complicated model efficiently, I have found there's probably 5 to 10 analysts that are doing more complicated models and have no clue what they're doing and are not showing proper, they're missing the boat on proper analysis. Simple models are the best model for most analysts until you've developed your skills and capabilities, and so that to the point where your judgment is improved so you can identify which kinds of problems require or can benefit from a more detailed analysis, and only using those more detailed methods and idealizations when you have a specific purpose in mind. Usually you can get it done faster with a simpler model. So now let's take a look. Now that we have these other capabilities, we've got some of the material properties in here. That's the main difference. More properties, more material information about the card. Let's look at how our results look now for this model. Remember, this model is identical to our earlier model, except that we have these allowables in there and some torsional constants that we're actually not using. You're looking at the displacements, we'll notice that these are identical to what we saw in our prior model. When we look at the forces at the constraints, those are our reactions, these are identical as they should be. Our forces in the rod elements, also identical because we have the same model. The fact that we put in a torsional constant doesn't affect anything because there's no torsion on any of these elements. But next let's look at the stresses. And let's look at the stresses that we saw before. Now before in our stress call out, it looked like this, where we just saw the stress on the element, and this is the axial stress for each element in the model. There were no margins of safety because we had no allowables information in our material card. But now with this model's run, we have the material card allowable information, and so our stress output is going to look different. It's going to look like this. Now notice, if you look at these details, the stresses are identical as they should be because we didn't change any of the loading or properties that matter in this particular case. But notice now the margin of safety column is populated. What NASTRAN does is it looks at the stress, it sees its tension, so it takes the tension allowable, which is 80,000 psi, divides by the stress in the rod, the axial stress in the rod, which is 1,273 psi, minus 1 gives you the margin of safety, which is enormous. In this case, we call it high. Instead of writing that margin of safety 62, we just say high. And then the next one is also tension. It writes the margin of safety the same way. That's in rod 3. In rod 2, that rod is in compression as it should be. And because it's in compression, NASTRAN writes the margin of safety relative to the compression allowable now. So what it does, it looks at rod 2's material card, and instead of putting in the compression allowable, we put the compression buckling allowable, so it writes the margin of safety against that. So that is the difference now. We now have margins of safety instead of the no margin of safety, and all that was just by putting in allowables. Got that? All right. So let's take a look. Let's think about kind of some ideas behind what we've learned. If we look at these two models, can you tell a difference? If you look at this, say, well, they look kind of the same. We got the same dimension here, here, and here. Okay, we got the same grid point IDs. Great. This is the same, but notice this is on a roller and this is on a pin. That means this is free to move vertically and this is not. This may look like not a big difference, and if somebody is not paying attention to detail, then they will miss this difference. However, these two models will give completely different results, because this one is free to rotate, which means this force is going to pull this down and going to tend to stretch these two elements, while this one is going to actually keep this element from lengthening, so it's going to change the way this model behaves. We're going to get different answers. So it's critical to pay attention to detail. A lot of engineering is careful attention to detail. And things like this, not paying attention, can make you create a model with glorious work and effort that's completely wrong. So you have to pay attention to these details as an engineer. Okay? So these two models, we see that constraint looks like the difference. Okay, next idea is let's take a look at the grid point singularity table. We've been talking about constraints and how they're handled. Let's go back to this model we were looking at before, and our CROD model had these SPCs tying in these different points. Now, if instead, let's say we had called out this same SPC card, but we're only calling out, let's see, at grid point 1, that's here, we're only constraining it in the X direction. At grid point 2, we're constraining it in the 1 and the 2 direction, the X and the Y direction, okay? So this one called out a bunch of other constraints that we didn't appear to need, while this one is calling out only the constraints that we think we need. This brings us to the idea of the grid point singularity table. If we had used this other model without all these extra superfluous degrees of freedom purged, we would have gotten a table like this. This is called the grid point singularity table. Singularity is when something goes crazy numerically. Now what happens is NASTRAN, when it's creating its matrices trying to solve it, if there's any singularity in the table, it can't solve it. And so what it does is it has a mechanism to turn off, to ignore singularities and basically purge them from the solution. When it does, and that's actually the default for a NASTRAN run if you're not keeping it from doing that. So what happens is if we had used these other SPC callouts that didn't have all those other degrees of freedom, we would have got a table like this. Notice it's going to call out each grid point with a soft or singular point, something that doesn't have enough stiffness. Singular meaning if there's no stiffness, then any applied load has enormous or infinite style deflections. So what NASTRAN does, it looks at a stiffness ratio of each degree of freedom versus other degrees of freedom. And if it's too low, meaning it could be singular, it's going to purge that from the solution. If you are also studying my Fine Elements by Hand course, you realize that we're going to purge certain things when they're constrained. We're going to move them from the solution. And NASTRAN will do something like that, where it purges or removes from the solution soft elements. Now, normally, if it's soft, you want to see because it's going to deflect. But this is so soft that it's problematic, and it doesn't actually, it actually is undermining your solution, keeping you from getting solution. So it just purges it as if it doesn't matter. So we purge things when they can't move, and we purge them when they aren't relevant. So purging everything in the Z direction makes sense because it's not relevant for this problem. Purging any kind of other kind of degrees of freedom can do the same thing. So here we're going to see in this grid point singularity table, we see this is calling out all three nodes because all three have some singularities. It shows what kind of point that is, they're grid points. It says it fails in the 3, 4, 5, and 6. It fails in the Z, torsion about the X, torsion about the Y, torsion about the Z. Grid point 1 fails in all those degrees of freedom, all those directions. Why? because there's no elements providing stiffness in the Z, no elements providing stiffness about the X or about the Y or about the Z. So it fails. And what it does, this little asterisk over here means that it purged it, which means A, it found a soft spot in your model that would undermine the solution and it removed it from the solution. Did the same thing for the 4, 5, and 6. At grid point 2, we see the same thing at grid point 3. So what each of these do is it has stiffnesses that are causing a singularity, which means a mathematical problem cannot be solved. So NASTRAN purged it, and the way it warned us that it's purging it is by reporting each grid point what the failed direction is, and that little asterisk means it removed it from the solution. Okay? This is fine in this case because none of these soft spots are affecting our solution, but it can screw up your results. So you need to be proficient at kind of looking to see, is this doing what we want it to do? Okay? So this is, there's actually a lot more that can be said about the stiffness ratio and about what sets that's placed in and all this. But for the novice and for actually most analysts, this is probably enough to warn you about this. And this is the reason why we provided all those other degrees of freedom in the way we ran the model, because then we didn't get this grid point singularity table. We purged those stiffnesses ourselves so we can be confident with our results. Now, the reason this purging of these singularities is important is because this is a little simple model. We can easily identify those stiffnesses that are problematic. On a big model, it's going to be very difficult to spot all the places that need to be constrained. It can be even more difficult to try and constrain them once you've noticed where they are. So actually, we can use this feature in NASTRAN, which can be controlled with the AUTOSPC card. We'll talk about that later. We can use this feature to allow NASTRAN to get rid of those soft spots that aren't relevant. But we need to use diligence to check this table and say, oh yeah, this makes sense. Oh yeah, it makes sense that it failed in this direction. Yeah, that won't affect anything. Otherwise, we could be getting erroneous solutions without knowing it. Okay, this is how we can use, so that brings us to the point of the SPC card. The AUTOSPC card is a parameter card. You can activate this card by just in your bulk data section, you can put param, that calls it out as a parameter, AUTOSPC, and yes. If you say param, AUTOSPC, yes, with commas between, or what that does is it says you're going to use this parameter, and this parameter is going to purge your degrees of freedom. If we had included this statement in our model, we would have got this grid point singularity table. Okay? However, parameter AUTOSPC, yes, is the default for NASTRAN, which means if we don't have the parameter card, we're still going to get this table if there's a soft spot in our model because NASTRAN is going to automatically purge those. Now, there are a bunch of versions of NASTRAN out there. We're talking about MSC NASTRAN here. Most of the others should be identical, but it is possible if you're using some other version of NASTRAN from somebody, it might not use that as the default, but in general, NASTRAN does, okay? Yeah, and this is the warning we were talking about before. If we use this parameter AUTOSPC equals yes, or just allow it to default, that can actually end up constraining nodes that actually are soft and should be soft. So it's a mixed bag of worms. So you need to keep an eye on this singularity table, grid point singularity table, to make sure that the places where NASTRAN's purging degrees of freedom are places where you want. Once again, you look at the grid point ID, what direction did it fail at, and it doesn't make sense. So at grid point 1, that's here, 3 degree of freedom, that's out of plane. We have no stiffness there, so it makes sense that it's gone. And same thing for node 2, node 3. There's no rotational stiffness for any of the elements, and that won't affect anything for this model. No rotational stiffness on any of these points won't affect anything. No rotational stiffness won't affect anything. Now, if we had a beam model, we probably wouldn't want it to purge that 6 degree of freedom because our beam elements can translate moments. Okay? So it's situational. All right, if we want to stop the AUTOSPC card from doing that, we can do that by specifying the AUTOSPC card and just say no. Remember, the default is yes. So if you don't have the SPC card, the AUTOSPC card, it's the same as putting param AUTOSPC yes. If we put no, it won't constrain those. In this particular case, it will tell it, you'll notice there's no asterisk, which means it wasn't constrained. It is possible the model will fail. It is possible the model will run. You're now rolling dice to see if NASTRAN will give you results. Okay? And in this particular case, NASTRAN did run. It won't always. All right. Next idea. Let's look at torsion. We said that CROD elements have torsional capabilities, so let's take a look at that. We have the same model as before, but instead of an axial load, we have a torsion. We can use our CROD. We could use either of our two element styles. We have all the same properties. The only difference between this model and our prior model is there's no force card. Instead, there's a moment card. The moment card is part of set ID 1, so it's going to be applied. It's located at grid point 2. It has a magnitude of 700, and it's pointing, the orientation is the 1, 0, 0. So it's pointing right down the 1 direction. Okay? Our results look identical to before, except now we're getting the results for the different model, the different loading. Our displacements, all we get is a rotation at that second node about the x now that's proportional. You can actually calculate this the angle of twist, TL over GJ. You can actually easily check this by hand. You've got your constraints, which should be the opposite of that applied torque. You have the forces in the rod element, which happen to just be a torque now, and stresses. And because we have the shear stress allowable, and we have the stress recovery coefficient, right? Here is our J, and this is the stress recovery coefficient. So this is a 1.0, which means this is like a 2-inch diameter shaft. So the radius, so when it does TC over J, it's going to be T torque times this value here, that stress recovery coefficient, which is the radius in this case, over the torsional stiffness. And that gives you your stress compared to your FSU, which is specified right here. It gives you your margin of safety. So there you have it. That's the basics of using the CROD element in a finite model. Now, if you look at the other subpart videos that we have here in Lecture 2, subpart B, C, so whatever, we're going to look at the CROD element. We're going to look at how to apply thermal loading to a model, using it to a CROD model, and we're going to look at replication on a CROD model. So stay tuned. You'll want to probably watch these videos in order unless you're already a NASTRAN expert and just looking for specific information. Enjoy.